Welcome to our fifth learning workshop for Chemistry 1405. This one is going to focus on Lewis structures and molecular geometry. So let's dive into this. First things first. Lewis structures are basically our way of representing molecules that show the valence electron. And this is obviously, of course, an imperfect representation, but it's a good symbol notation to help us to understand valence electrons and what role they play in chemical bonding. Now, for ionic Lewis structures, it's kind of a different animal. It's a little bit simpler, and what we do is basically use the atomic Lewis structures, and we show how electrons are transferred to form the ionic compound. So, as you can see, there's several different examples here. There's sodium and chlorine. Sodium has a +1 charge, or rather, sodium does not have a +1 charge initially. Sodium actually has one valence electron, and chlorine has 7 valence electrons. So sodium will transfer its 1 to chlorine, and then you will get sodium chloride. And it's a similar thing. And these actually, honestly, these examples are not super great because I don't like the fact that they show the charges first. So I'm actually going to cross these examples out. We're going to actually do better examples. Okay, so let's take a look at lithium and chlorine. So lithium is what element? What elemental symbol? And you can just type it into the chat if you wish. So lithium is what elemental symbol? Yeah, Li. So if lithium is Li, and then lithium is how many valence electrons? 1. Very good. And then I'll draw the 1 valence electron as a circle like this. And then we also have chlorine, which is the neutral atom as shown above here, has 7 valence electrons. Okay, so here's the deal. What happened, I'm going to change colors just to emphasize what's happening here. Lithium is going to transfer and give its electron to chlorine. That is going to result in an ionic bond. Well, actually, what it results in ultimately is 2 ions which then stick together, forming the ionic bond. Because all an ionic bond is an ionic bond is simply the electrostatic force of attraction between a positive charge and a negative charge. And so chlorine here is going to have the I'm thinking about how I want to write this. I think I'm actually going to write it like this. It's probably more appropriate to write it like this. I have Li with no valence electrons and a positive charge. And then I have chlorine that has all of the valence electrons around it. The 1 it took from lithium, plus the 7 it started with on its own. And there we go. And so that is the, I guess you could say the Lewis structure for lithium chloride, for ionic lithium chloride. And the formula would just be LiCl, of course. That was really sloppy. Sorry. Let's skip down to one that's a little bit more complex. Let's skip down to one like aluminum and phosphorus. So aluminum, of course, is Al. And how many valence electrons does aluminum have? Yeah, 3. And phosphorus, how many valence electrons does phosphorus have? Yep, phosphorus is 5. So I'll go ahead and draw phosphorus here. One, 2, 3, 4, 5. All right, so here's the deal. What you're going to see here, I'll go ahead and change the color. Aluminum has 1 electron transferred up here, and 1 electron transferred here, and 1 electron transferred here. So aluminum is going to lose all 3 valence electrons, phosphorus is going to gain all 3, and you're going to end up with aluminum with a 3+ charge, and phosphorus with a full octet around it, and that would be a 3- charge. And so once again, that's just going to be a very simple formula, ALT. Okay. Well, what if we had something like aluminum and sulfur? With this, aluminum still has its 3 valence electrons. 1, 2, 3. And let's do a sulfur. Sulfur is 6. 1, 2, 3, 4, 5, 6. Okay, so here's the deal. Aluminum is going to lose 1 electron to here. Lose another electron, or another electron here, but it can't give 3 to this 1 sulfur because the sulfur doesn't have 3 places to accept it. So I have to draw another sulfur. And so I'll do another 2, 4, 6. Well, now this aluminum can give its last electron away to the sulfur, but this sulfur is now missing a place to put its, or it's still missing a full octet. So I have to grab another aluminum then. So this aluminum has 1, 2, 3 valence electrons, okay? So now this one, I'll use a different color for this. This aluminum can give its electron to this sulfur, but it still has 2 more valence electrons to give away. So I have to draw another sulfur. And that sulfur, of course, has 6 valence electrons, just like the other 2. So this can transfer this electron here. This can transfer this electron here. And now that sulfur is happy, the aluminums are happy, everything is fine. I now have 2 aluminums with 3 plus charges and 3 sulfurs with 2 minus charges. What's tricky is like, how do you want to draw this? Well, I can draw aluminum, I can draw a sulfur, with a full octet, and that is a 2 minus charge. And then I can draw another aluminum with a 3 plus charge. And if I want, I could draw the sulfur on either side of the aluminum, or I could even draw the sulfur above it if I wanted to. It doesn't really matter too much. Just generally speaking, if you understand that the negative charges are going to not want to be right next to each other, and the positive charges are not going to want to be right next to each other. So if you kind of alter positive and negative, you should be in good shape. Now, I will say this. Very few teachers really have you do much in the way of drawing ionic Lewis structures, because there's a limited benefit to drawing these out. I mean, they don't really necessarily provide you with a ton of information, because the crystal lattice structure of it generally tends to have to be determined experimentally anyway. So, but in this case, we see clearly that this is going to be Al2S3. Does that make sense? Do you want to try one on your own, or do you want to just go ahead and skip to the molecular Lewis structures? Yeah, absolutely. Let's have you do uh, let's have you do rubidium and oxygen. Or rather, no, sodium and phosphorus. Let's do that one. Sodium and phosphorus. Ooh, coincidentally, if you want to draw on my cool Lucid Spark board, I'm going to go ahead and share the link with you, and you can actually jump on the Lucid Spark board and you can draw with me. That's an invitation for you to draw on the online interactive whiteboard I have here. And the reason I end up using Lucid Spark is because it's a lot better than the built-in Blackboard. Yeah, you can create an account with your TCC email, like the my.tccd.edu. It's free, and they don't send you like spam or anything like that. If you don't want to, you don't have to. But it's kind of a cool thing for like collaborating and working with others. Like if you have school projects and such. And it's really good. It's much better than like the whiteboard in the Collaborate app. It just draws a lot smoother. Plus, you can type in it and you can adjust the font, and you can add images and PDFs and other things like that. Good, that's good for sodium. Excellent. Phosphorus has 5 valence electrons. Good deal. Now, is the phosphorus completely satisfied? Does it have a full octet yet? Or do we need more sodiums? There you go. And is the phosphorus satisfied yet? Sorry. And you can draw up here too if you want to. Like, want to draw that last sodium. You could draw it up there if you wanted to. Just because there's room. There you go. Now is the phosphorus happy? As happy as it's going to get, right? Yep, it's good. Three sodiums for 1 phosphorus. The sodium was missing 3 valence electrons. It needed 3 to form an octet, so it took 1 from 3 different sodiums. Now it's happy. It has a full octet. Very good. Um, yeah, I was not consistent. Yeah, I would say put it on the outside. Yeah, it's tough drawing with these, drawing on the computer. No matter what you do, it's definitely tricky at first. Now, admittedly, it might be better to have the last sodium on the right side, so it's not next to 2 other positive charges. But that's pretty good. You have the idea. Okay. Yeah, like that. Very good. All right, cool. So now we have the idea for that. Now let's go ahead and take a look at formal charges for how to do Lewis structures for compounds that are molecular in nature. So let's look at the first one, silicon dichloride. There's several steps to drawing Lewis structures here. And I'll go ahead and type them out so you have a clear idea of what they are. So step number 1 is count the total number of valence electrons. And I will say this is simply one method out of many for drawing Lewis structures. I just find this one to be one of the easier ones to consistently and correctly always get accurate Lewis structures. So if I count the total number of valence electrons, if I'm looking at silicon, silicon tetrachloride, silicon has 4 valence electrons based on where it is. And chlorine has 7, but there are 4 of them, so I'm going to take 4 times 7. And then I add that together, and if I add 4 plus 4 times 7, I should get a total of 32. So this is 32 valence electrons. 32 valence electrons. So now what I'm going to go ahead and do is step number 2. I will draw a skeleton structure. So what is a skeleton structure? Draw a skeleton structure. And a skeleton structure is basically you show how the atoms are connected with only use single bonds and don't show any lone pairs. So that's a skeleton structure. So in this case, the skeleton structure for silicon tetrachloride, usually the first atom listed is the central atom. So when I see silicon listed first, that means that's the central atom. That's going to go in the middle. Okay. And then I'm going to draw, connect it to 4 chlorine atoms. So 1, 2, 3, 4. Now there are different ways of representing bonds in Lewis structures, but the most common and indeed I think the clearest is to draw a bond as a line. Now you have to understand what is meant by this short line connecting silicon chlorine is that this is a shared pair of electrons. So it's actually 2 electrons, and I'm only drawing these 2 dots for effect. So you wouldn't necessarily have to draw these normally. But each one of these bonds is a shared pair of electrons. There's 2 electrons shared between the silicon and the chlorine. So this is my skeleton structure. Shows how the atoms are connected with single bonds. Okay. So then, step number 3. Step number 3 is place the remaining electrons in pairs, and I emphasize that with exclamation, in pairs on atoms that do not already have a full octet. Okay. I'll place my remaining electrons in pairs on atoms that do not already have a full octet. So and I should emphasize also, I didn't mention this, start with the outer atoms first. Share with the neighbors, as they say. So start with the outer atoms first. So in this case, how many valence electrons have I used up in my skeleton structure? What do you think? How many valence electrons have I already used? 8. Yep. So if I subtract 8 from 32, let's take 32 minus 8, that's going to leave me with 24 electrons, right? So then I'm going to place my remaining electrons in pairs on atoms that don't have a full octet. So I'll start with my chlorine. I have 2 here, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, keeping in mind that the orange bonds, those shared pairs of electrons, they account for 2 for both the chlorine and 2 for the silicon. Okay, they count 2 for both the chlorine and the silicon. So, tell me what you think. Are the chlorines happy? Do they have 8 electrons around them? What about silicon? Is silicon satisfied? Does it have 8 electrons around it? Okay, good. So all of the atoms are happy. All of them have full octet. Therefore, this is a good Lewis structure. This is, in fact, the best Lewis structure for silicon tetrachloride that we can draw. And, in fact, because it's the only Lewis structure that we are capable of drawing, so it does not have any resonance structures. All right, so we don't have to go any further than that as far as steps for drawing our a good Lewis structure. Let's skip over to number 4. Number 4 is going to present a little bit more challenge for us. So this is CO3 with a 2 minus charge, and it looks like I actually mislabeled that. I'm going to go ahead and fix that. CO3, not CO2. 2 minus charge. Okay, so how many valence electrons for carbon? How many valence electrons does carbon have? That's right, 4. And how many valence electrons does oxygen have? Yep, that's right, 6. So there are 3 of them. So we'll put 3 times 6. 3 times 6. Now, it also has a 2 minus charge, right? So since there's a 2 minus charge, am I going to have extra valence electrons or am I going to have fewer valence electrons? 2 minus charge. I'm going to have extra. Very, very good. It's negative. Valence electrons are negative, so if I have a negative charge, that means I have extra valence electrons. This actually, have 2 extra valence electrons, so I'll add that 2 there. So 3 times 6 is 18, plus 2 is 20, plus 4 is 24. Add these up, you get a total of 24 valence electrons. Now I'm going to draw my skeleton structure. Carbon is listed first. I can assume that's the central atom, which means there's going to be 3 oxygens attached to that carbon. Now, how many valence electrons have I used up with the skeleton structure? 6. That's right. Each bond is a shared pair, 2 electrons. I have 3 bonds, so I've used up 6 valence electrons, which means I only have 18 valence electrons left. I will place those remaining electrons in pairs on atoms that do not already have a full octet, starting with the neighbors, right? So 2, 4, 6, 8, 10, oh, that was sloppy, 12, 14, 16, 18. Okay, cool. So here's the deal. Do my oxygens have, are my oxygens happy? Do they have 8 electrons around them? I've placed all my valence electrons. Are my oxygens happy? Yes. Good. Now what about my carbon? Is my carbon happy? Does it have 8 electrons around it? No. So if after placing my valence electrons, I see that I have less than a full octet, I need to go to rule number 4. And rule number 4 says, if any atom has less than a full octet, share a pair of electrons from an adjacent atom by turning one of its lone pairs into an extra bond. So what does that look like? Well, it looks kind of like this. I'll take one of these groups of valence electrons. Like I can do this. Actually, I can do it from any atom, really. All these oxygens are pretty much the same. So I'm going to go ahead and move those electrons and form an extra bond. And that extra bond, I'll draw in a different color here. And now I'm going to go ahead and erase the movement arrow because I know what I did. Does that make sense? Now, are the oxygens still happy? And what about carbon? Is carbon happy now? Does it have a full octet? Yep. So everyone is good. And that's it. Now, since this Lewis structure actually has an overall charge, when it has an overall charge, I put it in brackets, and I put the charge outside of it. So this is a 2 minus charge for this whole thing. And just for clarity's sake, I think I'm going to put it to a different color because I don't want it to be confused with this part up here. I'll put it in blue. 2 minus charge. There we go. Cool. Now, let's do SO2. You want to try to take a stab at it? There's 6 valence electrons for sulfur. Good. And there are 2 oxygens. Good. Each one having 6 valence electrons. And you get a total of 18 valence electrons. Very good. Now we've drawn our skeleton structure. And we've used up 4 electrons from our skeleton structure. And so we'll place our remaining electrons on the atom. And you're starting with the outer atoms, which is good. There we go. Hope you don't mind me narrating what you're doing. Okay. 2, 4, 6, 8, 10, and 12. So, do we have any more valence electrons to place? Actually, we do. You only used 4 in the skeleton structure for the bonds, and you've placed 12, so that 4 plus 12 is 16, but you have a total of 18. So where are those last 2 electrons going to go? Yep. Now, in pairs, they can't be one at a time. In pairs. You always have to put them in pairs. And the reason is because unpaired electrons are actually very unstable. You might have heard this term before and described by nutritionists and others, but the unpaired electrons are called free radicals. And free radicals are actually responsible for triggering various sorts of cancer to start occurring and all sorts of other unfavorable things inside your body, which is why we don't like free radicals. Generally speaking, neither does nature. It's not to say that they don't sometimes happen, but they generally aren't a very good thing. Nature tries to avoid them as much as possible. So, looking at you, so far your Lewis structure looks great. Does any atom not have a full octet? Sulfur. Sulfur is missing some electrons. It doesn't have a full octet. So what do we need to do? How can we fix it? Let's take that lone pair and make a second bond. Very good. Absolutely. Excellent. And that's exactly what we do. So now you have sulfur dioxide Lewis structure. Very nice. And while what the Lewis structure you've drawn is 100% correct, if we wanted to make it just a little bit more, shall we say, neat and clean, we might center those bonds and put them like here and here. But that is excellent. That's perfect. That's exactly what you want. Cool. Now, let's do one, let's do one, oh, before we do that, let's talk about resonance. Okay, so even though you chose to put the electrons from oxygen, share the electrons from the oxygen on the right, could you have shared the electrons from the oxygen on the left instead? Would that have been possible? Yeah, it would have been possible. Absolutely. So you could have shared it from the electrons on the left, or the oxygen on the left. And if you had, this is what you would have gotten. You would have gotten double bond over here, single bond over here, 3 lone pairs on this oxygen, 1 lone pair on the sulfur, 2 lone pairs on this oxygen. These two structures here, when you have double bonds, you can have what are in multiple ways. Usually when you have double bond, there's multiple ways in which you can show those double bonds, or multiple different um, places where those double bonds could have been from. In those cases, we call that, um, in those cases, we call that resonance. So this is one resonance structure, and this would be a second resonance structure. And the truth is that when, for the actual molecule is neither one of these two. The actual molecule is actually kind of a hybrid of all the different resonance structures that can be drawn for that molecule. So, and occasionally there are some resonance structures that are more important than others, but in this case, these two resonance structures are equally important. In other words, it's equally likely to be either one of these. And just like when you mix paint, if I mix red and blue, if I mix red and yellow paint, I don't get red and yellow switching back and forth between them, right? It's not flashing yellow then this time and then red the other time. When I mix red and yellow, I get orange, right? Same thing with these two resonance structures. If I hybridize these two, I don't switch back and forth between them. What I actually get is something that's kind of a hybrid between them. And that hybrid, I'm actually going to go ahead and draw the hybrid down here instead of the NCl. So the hybrid resonance structure for this would could actually be drawn like this. I could draw a dotted line to represent a partial double bond. It's not an actual complete double bond, but it's a partial double bond. And then I have this and this. And I'll be honest, they usually don't really worry about the electrons, because when you have resonance structures, um, these are the only ones that are stable. And of course, these electrons right here, I'm actually going to draw in a different color, orange. These electrons here could just as easily be over here. So almost kind of like a faded half electron pair, so to speak. But this would be kind of the resonance hybrid. Now, you won't be expected to draw resonance hybrids in all likelihood. But I just wanted you to understand, because sometimes they'll ask questions like, well, what does the actual molecule of such and such look like? And it might say it has a double bond on one side and a single bond on the other, or it has two bonds that are somewhat between a double bond and a single bond. Well, the answer would be it has two bonds that are somewhat in between a double bond and a single bond. It's not that there's a double bond on one side and a single bond on the other. Does that make sense? Okay, cool. All right, there's a couple other things I want to show you. And I'll mess this up. Okay. Okay. Now, next, we want to look at let's see. Let's do CS2. Let's do CS2. And so CS2. Do you want to tackle CS2 as well? Okay. Very good. 4 electrons for carbon. And there are 2 sulfurs, so 2 times 6. That's going to give us 16 valence electrons. We draw a skeleton structure, carbon, a sulfur on each side. Very good. That means we used up 4, which means we have 12 remaining. 12 valence electrons remaining. Oh, smart. Use the big dots. So 2, 4, 6, 8, 10, 12. Okay, that's it. So our sulfurs are happy, right? What about our carbon? Mm-hmm. So we have, it's a sulfur has 8 valence electrons, but carbon only has 4. So what are we going to have to do? Let's show them. Taking off one of those pairs of electrons, and we're going to make a bond. No, actually, you could make a solid line because that's a solid double bond. That's not a partial bond. And in general, when you're drawing Lewis structures, you don't show those partial bonds. That was just for the resonance hybrid. And I don't know, maybe I shouldn't have shown you that because I don't know if you're going to be expected to know that anyway. Sorry about that. All right. So now, is carbon happy now? No. So what do we need to do? Yeah. Yeah, we share another one. This time you did it from the opposite side. So question, could you have shared the electrons from the same carbon as, or from the same sulfur as before? Would that have worked? Yeah, you could have. So that would have given you a different resonance structure, right? So you could have had both pairs of electrons shared from the sulfur on this side. Now it would have given you this. One sulfur would have had 3 lone pairs. The other one would have had 1. Does that look? I mean, that looks a little lopsided, though, right? Which do you, or you could have done both from the other side. So if you look at these 3 resonance structures, which of these 3 do you think is probably the best resonance structure, or the most important resonance structure? Which of these 3 is probably most likely? Yeah, the middle one, right? Yeah, the one you did. Exactly. So all 3 of these are valid resonance structures, but this one is the best. The one you did was the best. Now here's the thing, there's a way to actually to kind of show that one resonance structure is better than the other, and it's called formal charge. So formal charge shows what charge each of the atoms would have if the bonds were completely nonpolar. In other words, if there was completely equal sharing, if they had the same electronegativity, if the bonds were completely shared equally, okay? What would the charge what charge would each atom have? And so there's a way you do that. The way you calculate formal charge is you take the valence electrons minus the designated electrons. So I'll show you what that means. So formal charge is equal, there you go, to valence electrons minus designated electrons. And what does it mean by designated? Well, when I say designated, this is kind of a term that I kind of came up with to describe the to describe the electrons designated to the to an atom in the Lewis structure. So this is electrons that are dedicated to a particular atom in the Lewis structure. Okay, so all lone pair electrons are dedicated to the atom that they're on. But for bonded electrons, I'm going to show the bonded electrons here. I'm going to put little blue dots. Okay, deep, 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 deep. Okay, so the bonded electrons, when we do formal charge, we kind of split them. Because half the electrons are dedicated to the one atom, half are dedicated to the other. So half of those bonded electrons are going to be dedicated to sulfur, and half are dedicated to carbon. It's like, for example, if you like, I don't know, when I was younger, sometimes my brother and I would pool our money together, and we would buy something like a particular toy, or like, say, video game or something. All right. So if we pooled our money together to buy this one game, we each owned half the game, but we weren't going to cut the game in half. So I mean, it was just understood. Half of it is mine, half of it is yours, and we both have ownership of it, so we can both share them. So we're both happy because we both get to play the game. Just like the electrons, both carbon and sulfur own the electrons. They share ownership, so they both have the electrons around, and so they're both happy. However, if we did like a legal separation of who owns what, the carbon owns half those electrons and the sulfur owns the other half. Just like I owned half the game, my brother owned the other half. Okay, so that's what formal charge is. It's more kind of like a legal, like, okay, who really owns these electrons? So I take the valence electrons that sulfur would normally have, which is, and I'll actually change the color here to a nice yellow. Sulfur normally has 6 valence electrons. But how many electrons does it have dedicated to it or designated to it in the Lewis structure? The one that you draw. Well, it has the 2 from the bonds, but it also has the lone pair electrons, right? That's a total of? What's that a total of? 8. So it's can you see my little arrow? Or like, I'm trying to see if I can. I have 1, 2, 3, 4, 5, 6. So there's the 2 lone pairs, that's 4, plus there's the 2 half of the bonded electrons, that's another 2. That gives me a total of 6 electrons around sulfur. 6 electrons designated to sulfur. So I take my valence electrons, which is 6, and my dedicated electrons, which is 6, and I get a formal charge of 0. That sulfur has a formal charge of 0. On the other side, if I split the other bond, how many does carbon have around it? Four. So carbon normally has how many? What's the normal number of valence electrons based on the periodic table? Yeah, 4. So for carbon, valence electrons 4 minus dedicated electrons 4. It's going to have a formal charge of 0. And then if you look at the sulfur on the other side, sulfur normally has 6 valence electrons. How many valence electrons does it have dedicated to it in this Lewis structure? 6. So 6 minus 6 is going to be 0. So your most stable Lewis structures are going to have formal charges as close to zero as possible for all of the atoms. Okay? Close to zero as possible for all your atoms. If I look down here at this one, the one below it, and I split my bonds here. Okay. This sulfur on the left has 6 valence electrons normally, but how many electrons does it have designated to it in this Lewis structure? 7. So this one's 6 minus 7, which means this formal charge is -1. It has more electrons around it than it would normally have if it was by itself. And what about carbon? Normally it has 4. How many does it have dedicated around it in the Lewis structure? 4. So this carbon still has a formal charge of 0, so that's good. And then what about the sulfur on the other side? Normally the sulfur has 6 valence electrons, but this one on that side has how many dedicated electrons? 5, yep. And so that's going to actually be 6 minus 5, that's a +1 formal charge. So with this bottom one, it has a +1 formal charge. On this one, has a -1 formal charge on this sulfur. And so that's much less stable because I'd much rather have my charges to be balanced. Non-neutral charges are unstable. And the same thing, you'd have actually the opposite situation up here. The +1 formal charge would be on this sulfur, and the -1 formal charge would be on this sulfur. You'd have a very similar thing happen. So that's one of the ways in which you can tell one of the Lewis structures is more stable than the other. I'm going to actually do one more example, and then I want to talk about molecular geometry with you, okay? The example that I'm going to do is SCN, or NCO. That's a good one. I like that one too. I'm going to actually do this. There we go. So there's an NCO minus ion. Okay. Now the way a molecule is written typically indicates connectivity. What that means is it shows how the atoms are connected. If I see an SCO or NCO or an SCN minus, it tells me nitrogen is connected to carbon, which is connected to oxygen, or sulfur is connected to carbon, which is connected to nitrogen. I'll do the NCO one. So nitrogen, so first I'm going to actually calculate my valence electrons. Nitrogen has 5, carbon has 4, oxygen has 6, and a negative charge gives me an extra 1. So that's going to give me a total of 16. 16 valence electrons. I will now draw my skeleton structure. N is connected to C, which is connected to O. Alright, so I've used up 4 valence electrons. So now that I've used up 4, I have 16 minus 4, which is 12 valence electrons left. I'll place my remaining electrons in pairs on atoms that do not already have a full octet. So let's do it. 2, 4, 6, 8, 10, 12. All right, so in this case, I have a carbon that's not happy, right? So I have to share a pair from an adjacent atom. So I'll go ahead and I'll erase my oxygen ones, and I will put an extra bond here. But carbon's still not happy, so I'll erase my nitrogen ones, and I'll put an extra bond here. Now everyone's happy, right? Looks awful similar to the one you just did. The only thing is that this molecule is not symmetrical. So we're going to go ahead and then look at, we're going to go ahead and we're going to draw our remaining resonance structures. Because remember, just like the other one, we could have, if we had wanted to, shared 2 pairs of electrons from the oxygen, couldn't we? And only 1 pair from the nitrogen. And likewise, we could have shared 2 pairs from the nitrogen and only 1 pair from the oxygen. And no pairs from the oxygen. And if we did that, that would give us, this one would have 3 lone pairs on nitrogen and 1 on oxygen. This one would have 3 lone pairs on carbon, or on 3 lone pairs on oxygen, rather, and only 1 lone pair on nitrogen. So let's do some formal charges. What would the formal charge be on the nitrogen in the top Lewis structure? So the one with 2 double bonds, what would the formal charge be on the nitrogen in that Lewis structure? What do you think? -1. 5 valence electrons minus 6 designated, so that's going to be -1. And the formal charge on the carbon? And the formal charge on the oxygen? Yeah, 0, right? All right, now what about the next one? What would be the formal charge on the nitrogen for the middle Lewis structure? The middle Lewis structure. Yep, -2. Very good. So you got this formal charge stuff down already. That's good. Most students don't pick it up that quickly. All right, what'd you get for carbon? 0. Okay. And what did you get for oxygen? 0? Not 0. Yeah, +1. Very good. Now let's do the last one. What's the formal charge on the nitrogen for the last one? 0. Yep. And what's the formal charge on the carbon? Also 0. And what's the formal charge on the oxygen? -1. Very good. So this is going to be a -1 over here. Okay, so we have 0, 0, -1, and -2, 0. Oh, yeah. Okay, so which Lewis structures of these 3 is the worst? Is the one that's least helpful in determining how the molecule will behave? Yeah, the middle one. Which one is the best? Or are the last 2 the same? Oh, good. Yeah, you suspected a trick question. Yeah, it's the bottom one. The bottom one is the best, and the reason is this. Both the top one and the bottom one are close to equal in stability in terms of if you just look at it in terms of formal charge, they both have one atom with a -1 formal charge and the rest of them are zeros. But when you have a choice of where to put the negative formal charge, it is always more stable to have the negative formal charge on the atom with the higher electronegativity, on the atom with the greater electronegativity. Now, have you learned about electronegativity yet? Have you gone over that yet in class? Yeah. So electronegativity increases as you go up, and it increases as you go to the right. So electronegativity of oxygen is definitely greater than that of nitrogen, and therefore the oxygen will be the one more stable with the negative charge. So excellent. I am so proud of you. That's awesome. You nailed that. All right. So that is how you do formal charges. So now let's take a look at a little bit with molecular geometry. So I am going to share an additional image here. And this is actually from, well, it's actually from one of the other classes where I have a review guide for. It turns out that when you draw these Lewis structures, they can help you figure out what the shape of the molecule is based on the Vsepr theory, which is the valence shell electron pair repulsion theory. Now, the valence shell electron pair repulsion theory basically states that atoms will try to be or electron groups will try to be as far away from each other as possible in order to be as stable. In other words, to be stable, because electron groups are made up of electrons. Electrons are negatively charged, and negative charges repel one another, right? So if you look at this guide, it shows that if you have two electron domains, can you see where I'm pointing to now? I just imported a new file from the bottom. Can you see the little table with the images and the electron domains? Okay, cool. So basically, if you have two electron domains, they're going to be as far away from each other as possible, and that's going to cause this to be linear. If you have three electron domains, they're going to be as far away from each other as possible, so they're going to kind of stick out as three spokes, but the molecule is going to be flat. It's going to be flat, but they're going to be sticking out as far away from each other as possible at 120-degree bond angles, and that's called trigonal planar. If you have four electron domains, then you're not going to be planar anymore, because if you had four in a plane, it'd have to be 90-degree angles. But it turns out if you put them at in a three-dimensional shape, you can get a bond angle of 109.5, which is only a little bit worse than 120. And in that case, you get a tetrahedron, tetrahedron, and that basically is called tetrahedron tetrahedral because if you drew lines and you covered plates with each one of these different things, you get a four-sided triangular object, which would be a tetrahedron. A four-sided triangular object would be a tetrahedron. So this is tetrahedral. And then, of course, if you have 5 electron domains, it's trigonal bipyramidal, and 6 octahedral. So what is an electron domain? Well, an electron domain is a bond. It can either be a bond, a single bond, a lone pair, or a double bond or a triple bond. So an electron domain is ... It can either be a single bond, a double bond, a triple bond, uh, or a lone pair, a lone pair of electrons. So a single bond and a double bond are, a double bond is only one electron domain, a single bond is only one electron domain, and a triple bond is only one electron domain. An electron domain is a region of electron density. It's a region of electron density. A double bond is only one domain because the electrons are in the same region. They're in the same area. So the double bond, the 4 electrons in a double bond are in the same area, so it's only one electron domain. So if I'm looking at, for example, this molecule right here, the one that we just drew a Lewis structure for, the NCO, how many electron domains are on that carbon? Just on the carbon. How many electron domains are around that carbon? Remember, a triple bond is how many domains? 1, 2, or 3? It's 1. So how many electron domains are around that carbon? 2, exactly. In that case, you could count on that molecule being what shape? There's 2 electron domains, that means it's going to have what shape? Linear. Very good. So now if you look at the oxygen, how many electron domains are around that oxygen? That's right, there's 4. So, but here's the thing. We would not use the oxygen to determine the shape of that molecule because oxygen is not the central atom. When you're doing electron domains, you always want to look at the central atom. What is the central atom? Is it is the central atom how many electron domains are around the central atom? That's what determines the shape of the molecule. The outer atoms are only bonded to one atom, so they really don't determine the shape of the molecule as such. Okay, so let's take that chart. You see, take that chart and let's use it to figure out what the shape of some of these other molecules we drew are. So what about carbon disulfide, CS2? What would the shape of that molecule be? What would the shape of CS2 be? Linear, yep. It has 2 electron domains around it, the central atom. The central atom's carbon, it has 2 electron domains, and therefore it is going to be linear. Let's take a look at some of the others. What about SO2? What about SO2? How many electron domains are around the central atom there? Oh, not 2. Oh, yeah, okay, did you say bent for SO2? Is that what you're saying? Bent for SO2? Or were you just asking generically about what about the bent molecular geometry? Oh, yeah. Okay. So if you look at the SO2, you'll see that it actually has 3 electron domains. One up here, the double bond here, and a single bond here. Now the electron domain geometry, because it has 3 electron domains, that would be trigonal planar. However, When one of the electron domains is a lone pair, when determining the molecular geometry, what we do is we ignore, we take the overall shape that you would predict from the from the electron domain geometry. In other words, we take this shape, the electron domain geometry says it should be trigonal planar. But since one of them is a lone pair, we take out one of those spokes. So I take out one of those spokes. So the remaining shape no longer trigonal planar because it doesn't have 3 spokes. It only has 2 spokes, so it would be bent. Does that make sense? So now in this case, you might actually have to distinguish here between bent with a 120 degree bond angle and bent with a 109.5 degree bond angle. In this case, this would be bent. It would be bent, but it would be 120 degrees bond angle. Now what about CO3? How many electron domains are around the carbon in CO3 2-? 3, that's right. And since there's 3 electron domains and they're all bonding domains, what would the molecular geometry be? Trigonal planar, very good. Now what about SiCl4? How many electron domains are around the central atom there? And therefore that would be tetrahedral. Very good. So this would be tetrahedral. Tetrahedral. And this would be trigonal planar down here for the CO3. Trigonal planar. Now, let's take a look at one more. I'm going to draw the Lewis structure for it just quickly because we don't have a whole lot of time left, and I want to kind of cover this. So NCl3, the Lewis structure would be nitrogen bonded to 3 chlorines. And if you did the Lewis structure correctly, you'd have 3 lone pairs on each carbon, or chlorine rather, and you'd have 1 lone pair on the nitrogen. So how many electron domains are around the central atom here? Central atom, of course, is the nitrogen. Oh, you may have already said it. How many electron domains are on the central atom? 4, exactly. But one of them is a lone pair. So if I scroll down to my shape here, I know that 4 should be tetrahedral, but if one of them's a lone pair, I have to ignore that. The remaining shape is what? What is that shape called? Trigonal pyramid, exactly. Does that make sense? Is that helpful? So, and likewise, for example, if you have water, so I'll go ahead and draw water real quick here. If I had water, H2O, I have oxygen here in the middle, and I have a hydrogen on either side, and I have 2 lone pairs. How many electron domains are around the central atom oxygen here? 4, yep. And so if I have two lone pairs, that means I'm going to look at the tetrahedral shape, but I'm going to ignore two of them. So I'm going to ignore two of the spokes. So I'm going to actually choose to ignore these back ones here. And if I ignore those two, the remaining shape is just this. And what would that be called? Yep, that would be bent. Only this time the bent would not be 120 degrees. This would be bent with a 109.5 degree bond angle. Now, did you did you go over the Lewis structures where you had a molecule that has more than 4 electron domains, like a 5 or 6, like trigonal bipyramidal octahedral? Okay. So you may not be expected to know those. If you did, well, tell you what, let me just go over one example with you, just in the off chance that you're going to be expected to know it or you'll learn it later. So there's one, we'll do ICl3 minus. Or actually, no, just ICl3. This is it. ICl3. Okay, so ICl3. I have 7 valence electrons for iodine. I have 7 for chlorine, and there's 3 chlorines, so 3 times 7. And that's going to give me a total of 28 valence electrons. What I'm going to then do is I'm going to go ahead and put iodine as my central atom. And because it's listed first, and I'll bond it to 3 chlorines. That's going to cost me 6 electrons because I've made 3 bonds, and I'll have 22 valence electrons remaining. So now I'm going to go ahead and place my remaining electrons in pairs on atoms that don't already have it. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Uh-oh. Iodine already has a full octet. Chlorine already has a full octet. There's no other place. I have 2 more valence electrons. I have to put them somewhere. If you run into a case like this, what you're going to do is you're going to place them typically on the central atom, if the central atom can handle it. Now, how do you know if it can handle it? If an atom is in the 3rd period or below, so basically sulfur or chlorine or below on the periodic table, then it can hold an extended octet. It can hold more than 8 electrons if needed. But so here's your Lewis structure for ICl3. Now you'll notice ICl3 actually has, oops, my bad. ICl3 actually has 5 valence electrons around the central atom, or rather 5 electron domains around the central atom. So that means that we would expect this to have an electron domain geometry that is trigonal bipyramidal. However, 2 of these lone pairs are, or 2 of these electron domains are lone pairs. So I have to ignore 2 of the spokes on this thing. Well, what do? Do I ignore the top and the bottom and make it trigonal planar? Or do I ignore 1 top and 1 side, 1 top and 1 bottom, or 1 top and 1 side, and it becomes like kind of like a weird, almost squared off shape? Or do I ignore 2 in the middle and it becomes kind of like a T? Well, it turns out in order to minimize the electron repulsion, with 5 electron domains, you always ignore, or you always cancel the equatorial positions first. the equatorial positions are the ones that are horizontal. So I'm going to actually cancel out not the top and the bottom, but the two that are on the side. And that's going to leave me with this remaining shape, which is called T-shaped. Kind of have to look at it from the side to see it as a T, but it's T-shaped. Now, if I had 3 electron domains, I'd ignore this one as well, and then it would just be linear. If I had only one that I needed to ignore, it would be what's called a seesaw. I'll actually show you kind of how that looks. If I was only ignoring one electron domain, I'd ignore this one here, and the remaining shape, if you turned it on its side, it kind of looks like a seesaw. If you know what the toy is I'm talking about, the one that has a little, connection, and then there's 2 little kids sit on either end of it. The little 2 legs down here, and they go up and down. So you have a little kid here, and you have a little kid here. You know what I'm talking about? Am I crazy? Does that make sense? So that would be a seesaw if you only had one lone pair but 5 total domains. But if you have, in this particular case with the ICL3, we actually have 2 lone pairs, so we'll cancel out these 2, and that'll give us this shape, which is T-shaped. So that's what we'll call it, T-shaped. All right, and I think that about does it. Now, if you want any more practice with this, or if you want to check out some more resources, let me go ahead and show you where you can actually find some more resources on this. I'm actually going to share my screen with you. I'm going to pull it up, share content. Nope, not that. Here we go. So if you want more practice problems with this, you can go ahead, or more anything with this. A lot of the stuff that we have on that is actually under general chemistry. You can find practice problems under molecular geometry. It's actually towards the end, molecular geometry and advanced bonding theories. So Lewis structure, molecular geometry and polarity, molecular geometry, etc. That'll be helpful. There's answer keys that go along with that. So, for example, you draw the different Lewis structures, indicate what the hybridization is, and the molecular geometries are all listed there. And this is basically the same ones that we did today. So you could actually check your molecular geometries with this. Furthermore, what might be even more helpful is the video tutorial library on this. If you go to the video tutorials under Chem 1411, and you go to molecular geometry and advanced bonding theories, there's some really, really good videos on the Vsepr theory, Vsepr theory, which is what we went over today in the molecular geometry. The trigonal bipyramidal family, it shows all the different molecular geometries associated with 5 electron domains. The octahedral family, all the electron geometries associated with 6 electron domains around the central atom. And then a variety of practice problems that he goes over. And so these first 6 videos are excellent, and I would highly recommend them if you're interested in learning a little bit more about molecular geometry. And also, of course, don't forget to come and visit us in the Science Learning Center. If you have any questions, we're always happy to help you out. And thank you so much for coming. We really appreciate it. Have a great night.